Physical science time. Today we're going to talk about centripetal force and projectile motion. So let's get started. So the first thing we're going to talk about, counter to what I just said in what order, the first thing we're going to talk about, I'm going to use this galaxy pin. The first thing we're going to talk about is projectile. Projectile. I don't really love that the mouse is still there, but whatever. Projectile motion. Projectile motion. So a projectile is an object that is flying through the air, right? And the hallmark of projectile motion, oh, there's a glare on my glasses. The hallmark, if you're like that. The hallmark of projectile motion is that the motion is composed of two components. It has an x component in the horizontal axis and a y component in the vertical axis. So when we throw something, the simplest way to represent this is something being rolled off a table. So we have some surface here, and the object, this little red ball, is being rolled off the table, and so it follows this path, right? So it has a horizontal component to its motion, and it has a vertical component to its motion. So like I said, this is a y component, and this is an x component. And projectile motion is interesting, and you can see this. I'm going to try to do it right here. Right, I don't know how well you can see that, but I'm going to do it more perpendicular to the camera. Back it up. There you go. It follows a curved path, as you know, and the curved path, any object does this, is because in the x direction it has a constant velocity. Oh goodness, let's spell it right at least. Constant velocity. And the constant velocity, we say sometimes, is even exactly the same as if we had rolled this object here. Just let's back it up a couple steps. This is my pantyhose ball. It's just a racquetball inside of some pantyhose that I use for this kind of physics demonstration. Anyway, the constant velocity is as if we had rolled it across a perfectly frictionless surface. So in the x direction, it has a constant velocity as if it's just rolling. In the y-axis, it is constantly accelerating. So its motion is changing, right? Constantly accelerating. And we know from the last couple of lessons that if something is accelerating, its motion is changing. If it's in constant velocity, is its motion changing? No. So no acceleration. Oh goodness, not acceleration. Let's erase that. There we go. No acceleration. If it's in constant acceleration, obviously it's accelerating. Its velocity is changing. In fact, both its direction and its speed are changing. It is constantly accelerating. So this has, yes, acceleration, right? It does have acceleration. So knowing what we know about forces and acceleration, are there unbalanced forces acting on it in the x-axis? No, because if there's only balanced forces, it is not accelerating in the x-axis. Whereas in the y-axis, are there unbalanced forces acting on it? Yes, because of what force? What force do you think is providing the acceleration in the y-axis? Well, there's one force that acts straight down all the time, and it is F sub g, as we talked about in the last lesson. So gravity is acting on this object, and in real life, air resistance and friction and all kinds of things are also acting on it. But when we talk about projectile motion, we say the only force, once it falls out of my hand, the only force acting on it is gravity. And so it has a constant acceleration downward in the y, as if it had just been dropped from free fall. Its y component is as if it's just dropped and falls freely. And then its x component has a constant velocity, no acceleration at all. And when we add these together, we get this curved path. This is if the object started out at a height. If the object is thrown upward, it follows this path. It follows a parabolic path. And so if it starts out here, and we impart some velocity on it, let me go back to red. If it starts out here, and we impart some velocity on it, it has some velocity, right? What's happening as it goes upward, right? I can't show this very well on video, but if we... Maybe you were able to tell. As as it goes up, it slows down. So its velocity is constantly decreasing. Until when we get to the height, it really has no horizontal velocity. V sub x equals 0. I'm sorry, V sub y. It has no vertical velocity. V sub y equals 0. If we throw it just straight up and straight down, at the top of its path, it has no velocity. Does that mean it's not moving? Well, at that split second, it's as if it's not moving. But then very quickly, it starts to do what? Well, as it goes down, its velocity is constantly increasing. So this is going to go back a couple of weeks. All these are velocities. It's going to go back a couple of weeks, but if we look at this image here, the parabola, if we look at the parabola, what direction is this accelerating the whole time? Well, when it's going up, it's slowing down. And when it's going down, it's speeding up. So what direction is the acceleration? Well, it must be opposite the direction here on this side. Its acceleration must be down. And then on this side, well, its acceleration is still down. And once again, that's due to gravity, right? So it has a constant acceleration down due to gravity, meaning that in this path it's slow. Speed up. It speeds up really quickly going down. And that's what forms this parabolic path. And in fact, if we correlate any point on the upward path and the downward path, all of this is negating air resistance. With no air resistance, if we correlate any path or any point, whether it's going up or down, it has the same speed going up as it does on this side going down. It's just a different velocity, right? It's going up this direction and down this direction. Projectile motion. Anything that's flying through the air under the influence of gravity undergoes projectile motion. If you have questions about this, leave them in the comments. Let's move on to centripetal force. So a key thing, I wanted this to erase the whole thing, clear the canvas. A key thing about, let's do this in a different galaxy color. Key thing about centripetal, ooh, that's nice. I started to spell it wrong, but it is nice. Centripetal force. Centripetal force. Ooh, that looks nice. So both of these things relate to how acceleration changes velocity, right? We saw in projectile motion that the acceleration was always downward, making the velocity decrease going up, and the velocity increase going down. Well, in this case, we're going to have a force, again, that's going to supply an acceleration. But in this case, and this is why I have the ball in the pantyhose, it is if I spin the ball, oh, I wish I could do it. There we go. Yeah, that fills up the little circle that my head is in nicely. So I'm spinning the ball, right? And it's very easy, and you've been on a merry-go-round, it's very easy to think that the ball's being pushed outward, right? When you're on a merry-go-round, you feel like you are flying out of the merry-go-round. That's something that's sometimes called the centrifugal force. And there's no such thing as a centrifugal force. Let's talk about that for a second. A lot of people will say that centrifugal force. The centrifugal force, there's such a thing as a centrifuge, which maybe you've heard of, but the centrifugal force, this means center, these are Latin words, center, fleeing. This is a force that makes us feel like our bodies are fleeing the center. Whereas in the centripetal force, once again, this is center, pedal means seeking. So the centrifugal force is real in the sense that you feel like it's true, right? It feels like you're flying off the merry-go-round. It feels like this ball is being pulled outward from the circle. But that's not really what's happening. Right? The centrifugal force is true as a feeling, but it's not a real force. So I'm going to erase centrifugal force. Just be aware that you might hear someone talk about the centrifugal force. You can feel the centrifugal force, but it's not a real force. And we'll talk about why in a second. So, it's called rainbow pin. Let's switch back to galaxy pin. So the centripetal force is really what's happening here. So imagine I'm swinging this ball, right? Here's my hand. That's me. Here's the pantyhose. Here's the ball, right? As I'm swinging it, if I were to let go at any second, what direction would the ball fly? So we're going to say I'm swinging it this direction. It's going around in a circle like that, okay? So if I let go right here, where would it go? Well, I don't know if you can see that, probably not, but it goes off in a straight line, right? If you let go at any time, it goes off in a straight line due to what? Why is this going off in a straight line? I hope you said inertia, because inertia is the right answer, right? If we let go of it, inertia takes over and it goes off in a straight line at the speed it had at that moment, right? So what causes it to stay in the circle? And if it's staying in the circle, what direction must the force be acting? Well, let's think about it this way. If we go from this second, this is time, sorry, that should be lowercase, time equals 1, and then at time equals 2, it's here, and at time equals 3, it's here. Well, how did the velocity change from there to there, right? It wanted to go this way, or inertia would cause it to go this way, and now instead it's going this way. And then in this one, instead it's going this way. So how is, thinking about acceleration, which causes velocity to change, how is it accelerating in each second? Well, it must be going inward, right? And you can even feel the pull on it as you swing it. It's going inward. The force, it's accelerating inward. And if it's accelerating inward, well, the force must be acting inward as well. So even though it makes the object move with a circular motion, what's happening here is actually the force is acting inward, and it's always even acting at right angles to the direction of, in this case, the string, right? The centripetal force always acts at right angles to the velocity. Centripetal force always acts at right angles to the velocity. So what makes you feel like you're flying off of a merry-go-round when it's being spun? The answer is really easy. You can say in one word, inertia. Inertia makes you feel like you're flying off a merry-go-round. Inertia makes the ball fly out of my hand when I let go of it. There's no centrifugal force. You're not really fleeing the center. It's just that when the force drawing you inward is gone, phew, off you go, right? There's a common experiment done, I don't know, maybe you had like a basket of flowers or something when you were a kid, you swing it around and, oh, the flowers stay in the basket even when it's up here. Why would that happen? Well, one word again, inertia, right? If you were to let go when the flower basket is at the top of the path, whoo, up they go, right, because of inertia. If you have questions about this, leave them in the comments. I think we've covered everything, so I will hopefully see you on Monday, and if not, I'll see you another time. Bye.